Now we will consider some examples of double integrals using polar coordinates. The first example is to integrate the function x squared plus y squared to the negative 3 halves, where P3 is the polar region that we defined in the previous video. So here, we're going to look at a double integral over the region P3 on the right, and we're going to do that by converting it to a rectangular region in polar coordinates on the left. So here, the radius is going to be between 1/2 and 1.5, and the angle is going to be between 0 and pi over 2. So let's just remind ourselves that we're going to have that r is going to be between 0.5 and 1.5, and theta is going to be between 0 and pi over 2. Okay, so we want to evaluate this double integral on this region of x squared plus y squared to the negative 3 halves dA. And we're going to do that by first looking at the function of x and y. We'll notice that it has an x squared plus y squared in it. And x squared plus y squared is in fact r squared. So when you see integrals that have x squared plus y squared in it, or multiples of x squared plus y squared, that's going to be a big hint that you're going to want to change to polar coordinates. So that's going to be r squared to the negative 3 halves. Now, according to our change of variables, dA in rectangular coordinates becomes r dr d theta. So here where we had dx dy, now we're going to have r dr d theta. My radius is going to go from 0.5 to 1.5. And then my angle is going to go from 0 to pi over 2. Now, what you see here is a function of r on the inside, the inner integral, and then just a d theta. So there's no thetas in this integral. So we're going to rewrite this integral as the integral from 0 to pi over 2 d theta, and then times the integral from, I'm going to call this 1/2 to 3 halves. R squared to the minus 3 halves, well, in fact, that's going to be r to the minus 3 dr. Okay. Now, we can first do the integral d theta from 0 to pi over 2. That's a simple integral. It's just going to be pi over 2. And then we're going to want to anti-differentiate here. So this is going to be minus 1/2 r to the minus 2 evaluated between 1/2 and 3 halves. So in fact, this is going to be, let's see, we'll write this actually as pi over 4 times a minus 3 halves to the negative 2, and then plus a 1/2 to the negative 2. We can do just a little bit more simplification. So we're going to get pi over 4. Okay. And let's see, 3 halves to the negative 2. Well, that's going to be, let's see, a minus. We're going to flip that over. That's 2/3 squared. So that's going to be 4/9. And then plus And let's see, 1/2 to the negative 2. So that's 2 to the 2. So that's going to be 4. Okay, we can do a little quick simplification here. I'm going to do pi times dividing everything by 4, negative 1/9 plus 1. So this looks like it's going to be 8 pi over 9. Okay, so that's a first integral that we've attempted by changing to polar coordinates. Here, it was a good idea to change the polar coordinates because the region itself was more easily described in polar coordinates, and the function that we wanted to integrate, okay, was radially symmetric. So when we changed to polar coordinates, it was a function of r and it did not depend on theta. Okay, now let's look at another example. Let's find the volume of a sphere of radius 1. So I want to look at the volume of a sphere of radius 1. And the way I'm going to compute that is I want to find the volume underneath the curve z equals plus or minus the square root of 1 minus x squared minus y squared. And so what I've done is I've actually drawn for you a hemisphere. And when I want to find the volume, call that volume V of the sphere, I'm going to do twice the volume of the hemisphere. So I would be doing twice. And then I want to integrate over, you can see that the region that I want to integrate over in the xy plane is the region x squared plus y squared is less than or equal to 1. Okay, so that's the region that I want to integrate. I'm going to actually show it right there. And so I'm going to think about this as just a double integral over that region. I'm going to just call it x squared plus y squared is less than or equal to 1 first. Okay, and then I'm going to show you I want to integrate the square root of 1 minus x squared minus y squared. Okay, so I'm going to integrate under z equals the square root of 1 minus x squared minus y squared. That's going to give me the volume if I integrate that dx dy. Now I want to show you what you have to do in order to change this to polar coordinates. Okay, you have to think about this circle, x squared plus y squared less than or equal to 1, or that disk. You have to think about it as being y equals the square root of 1 minus x squared on top, and then y equals negative square root of 1 minus x squared on bottom there. And so this integral, if I was to describe it in rectangular coordinates, would be an integral. On the inside, it would go from negative square root of 1 minus x squared, okay, to positive square root of 1 minus x squared. I would be integrating the square root of 1 minus x squared minus y squared. To describe it this way, I would be integrating it dy dx, because I'm going from y equals negative square root of 1 minus x squared to positive square root of 1 minus x squared, and then x would go from negative 1 to 1. So I guess it would have been better if I had written this as dx dy in the first place. Okay, so that looks like a terrible integral to have to do in rectangular coordinates. So what I would like to do is I would like to change this to polar coordinates. Okay, so I'm integrating over a circular region. Okay, so I'm going to integrate, okay, a circle is going to be a double integral. This is a circle of radius 1, so it's going to go from 0 to 1 in r and 0 to 2 pi in theta. What I'm integrating is the square root of 1 minus x squared minus y squared. That's 1 minus r squared. And then dy dx becomes r dr d theta. Okay, and this is a simpler integral to have to work with. Okay, so we're thinking about it kind of one-dimensionally. Here we have a z versus r graph, and we're thinking about this as being z equals the square root of 1 minus r squared. And that is what is giving me a volume that I want to find underneath. Okay, so I'm going to break this up into two integrals to make this easier. So one is the integral from 0 to 2 pi of d theta. Again, notice that the integrand does not depend on theta here, so I can just pull that integral out. And then this will be the integral from 0 to 1 of 2r square root of 1 minus r squared dr. Now, I brought that 2 inside. You'll see why in a second. I'm going to do a u substitution to do this integral of r in r, and that's going to be u equals 1 minus r squared, and then du is going to be minus 2r dr. Okay, so that's going to give me this first integral of d theta is going to give me a 2 pi. Okay, then I'm going to get a minus sign from the du, and I'm going to integrate. Let's see, 1 minus r squared is going to go from 1 to 0 now, and I'm going to integrate the square root of u du. Okay, another way to write that is going to be 2 pi times the integral from 0 to 1 of u to the 1/2 du. Okay, switching the order or of the limits using that negative sign. So this is going to be 2 pi times 2/3 times u to the 3/2 evaluated between 0 and 1. And so that's going to give me 4/3 pi, which is exactly what we'd expect for the volume of a sphere of radius 1, 4/3 pi.